どこに行きましょうか。屋根階で行ってないな。
And before I get going, I just want to say it's all a major collaboration with Brenda Andrews, who's the director of our institute here at the Donnelly Center. And I'm going to try and explain why this graph is a model of the cell. That's basically what I'm trying to tell you guys. And yeah, it could be anything, right? But here's the model that we have so far. And we know a lot of the parts of the cell, but we really don't have a good model for how they're integrated together. And omics, functional genomics, systems biology, tries to do that in a quantitative way. It's not that we're very good at it at this stage, but it's sort of the beginnings of it, and our project has kind of contributed to this. So I'm going to talk about the budding yeast, which a bunch of us work on here. Georgina and David are leaders in the field, and it's a eukaryotic cell, so it's a billion years further evolved beyond prokaryotes, and it's got a nucleus and a mitochondria with its own DNA. It's got all the goodies that we find in human cells, and so it's been a major model organism. And in fact, there's 1,000 yeast labs around the world, and they all feed data into one big common database that is put together at Stanford by SGD. So yeast has 6,000 genes and 16 pairs of chromosomes. And you compare that to a human has 20,000 genes, 23 pairs of chromosomes. So it's a pretty sweet little cell. And the yeast community, this international community, there's labs all over Europe, major labs in Japan, and of course in North America, and it's expanding to China and India rapidly as we speak. Not in Russia. There's nothing in Russia. I think it's weird. But anyway, the goal is to figure out, and so we've got a graduate student, there's 6 graduate students, we've got a graduate student for every single yeast gene, right? And you think that we can figure out how this thing works, this cell works, we can model it, but we're so far from it because we have to figure out how they're all connected to one another and how they're talking to each other, the dynamics of it all, and that is way beyond the capability of the yeast community, but any community studying any form of life. But just to give you a view of that, here's 16 chromosomes, each line represents a gene, so these genes are just lined up one after another on each chromosome. And one thing you can do with yeast, because it's so easy to manipulate this organism genetically, partly through homologous recombination, is we can go into a diploid, so just 2 copies of every chromosome, a diploid organism, and delete 1 copy of each gene. And then the beauty of yeast is you can take it and convert it from a diploid to a haploid, where it only has 1 copy of each chromosome. And you can, under those conditions, ask whether that gene is required for life. And so the yeast community did this, deleted each of the 6,000 genes one by one in a diploid, converted it to a haploid, and asked whether the gene was required for life. And 1,000 of the 6,000 genes, when deleted individually, is required for life. 5,000, you delete them, and the cell basically barely knows it's happened. Okay. And this is true not just in yeast, it's true in all forms of life, basically, any sophisticated form. So E. coli, in yeast, in worms and flies and mice, and in human cells, only a fraction of the genes are required for the basic cell division and replication of chromosomes. Most of the genes appear to be functionally redundant, okay, so that you can delete them, and they must be doing something because they're highly conserved, but it looks like there's a backup plan for whatever role this is. So a nice example is DNA repair. So there's many pathways that control DNA repair, different pathways, and they're required under particular conditions, but in a laboratory setting, you can remove non-homologous end joining, and the cell's perfectly fine to repair its DNA through homologous recombination, for example. But if you remove both those pathways, homologous recombination, non-homologous end joining, the cell has a problem. So we think many of the reasons these cells aren't required for viability is because the cell required with backup systems, and so that the analogy is it's like a finely tuned jet engine where if something goes wrong, we've got another way to keep the plane up in the air. So that's a good question. I can't figure that out except to say that it wants to streamline everything as much as possible, but still, then why would there be a backup pathway for that thing? And there's really only one proteasome. It doesn't make another copy of all those genes and another. I mean, there's other ways autophagy things to create proteins, but the major essential complexes are things like the ribosome, the proteasome, and whatever. Actually, you're not telling us that the yeast cell where you delete the 5,000 genes and then we make a life but that's not what Craig Venter tried to make the genome, right? And basically, they tried to take the equivalent of these 1,000 genes and see what are going to be the sequence, right? So, yeah. Yeah, I don't think it's the best way to think about it. I mean, it's way more complicated than just one graduate from my PhD at this point, and this paper from thanks Peter Novick and Botsy comes out, and they're looking for suppressors. This is a genetic interaction of these actin mutations, and so and this is a cell stained for filamentous actin with Freud. It's all drugs like stuff. Yeah, that's a good picture. Yeah, I know. Yeah, so of course David is the yeast action expert. But look at that. The mother cell, the daughter cell, they've got these patches here. David's going to talk about all endocytosis. And then these cables that are tracks for motors that are going up. And yeast only has one actin gene. Okay, so this makes it, and it's essential. If you delete it, you have any of these guys, the cell can't form any shape properly, and it can't divide. But and if you have a worm, a nematode, they have lots of different actin genes, and so you can't really do this type of experiment with a worm. So what Novick and Botsing did was they mutagenized the actin gene, and this -1 means it's a particular allele, so it's a particular mutation. And they actually made a mutation that was alive at 30 days and dies at 37. This is a temperature-sensitive mutant. And Case and Fly Genesis use this to study such genes in traditional ways. Look at this temperature and then shift to restricted temperature and see what happens. The essential phenotype. And there's lots of different things that happen. The protein might not be made, the restricted temperature might be degraded, but the classic idea is that you have a mutation in the polypeptide chain that allows it to fold normally at the permissive temperature, but when you put energy into it, the protein misfolds. And phenotype, there are examples of that. So what they did was they looked for suppressors of actin genes. And so what happens here is if you combine ACT1-1 and you basically select for a random mutation in the genome that suppresses this temperature sensitivity, and you identify a new gene that way. And so ACT1-1 plus this mutation, the cells are alive at restricted temperature, and we'll call this an example of genetic suppression. We call it a genetic interaction because it is an unusual phenotype. You go from dead to alive, right? That's pretty powerful. And since it's a gain of a phenotype, we'll call it positive genetic interaction. So when they did this, it was completely unknown. They wouldn't even have known what this gene is. It turns out that it's involved in phosphatidylinositol signaling, which is a signaling pathway that can regulate actin dynamics through proteins, but you probably still don't know the mechanism. But there's some major functional connection between these two genes. Okay. And this is not that case, but we've been studying some of this, but I'll show you a phenotype. So here's NEO1, and it's a temperature-sensitive mutant, so the mutant will grow at 22 degrees. It's totally dead at 38. And now if I take that TS mutation and delete another non-essential gene, YMR010W, perfectly alive at restricted temperature. These are powerful phenotypes. And in this case, I'll talk about later, NEO1 is a flipase that flips phosphotylserine ethanolamine from the outer leaflet to the inner leaflet, and this thing's probably a scramblase that antagonizes it. And if you just get rid of the antagonizing enzyme, then there's another backup flipase in there that can take over. Anyway, that's the kind of phenotype. So we have this genetic interaction, and then here's the fun part. Here's another allele of actin, so a different mutation in the actin gene, and when you take that mutant actin and combine with SAC1F6, the cells are dead. You get the permissive temperature. Okay. And again, I'm just trying to look at the mutations out if we understand any of this, right? We should look it up though, try and figure it out. Anyway, so this is an example of so this is a cool rescue positive genetic interaction. This is synthetic lethality, which is a negative genetic interaction. So, and this is a very famous one that I'm going to talk a lot about. But this is unusual. Mutation, this is viable at 20 degrees. This one's perfectly viable at 20 degrees, but the double mutant is dead. Okay. And this would suggest that these two genes are working together to control an essential function of the cell. Right? And presumably that's actin assembly. And this mutation compromises the actin gene itself. And then this mutation must, exacerbate that somehow and have something to do with all the full actin dynamics. Okay, so synthetic lethality is a very simple definition where it deletes one gene and the cells are viable, delete another and they're viable. The double mutant is lethal, and this is a rare event. If you take DNA and test all possible double mutants, you'll only find a few cases like this. And because it's rare, geneticists thought that this must be important and it must be telling us that these two genes are working together somehow in the cell. And what David did was he went into the literature and figured out that this combination of two mutations leading to a dead phenotype has a name called synthetic lethality, and it was coined by this guy Dobzhansky, who was a fly geneticist in the 40s. And so synthetic lethality occurs when a combination of two mutations either by itself or lethal causes lethality. And the wild thing is that Dobzhansky was working with flies from an outbred population, so he was going out into the wilds of California, isolating flies, crossing them to one another, and he could trace a defect in development to an allele of one gene from one parent and an allele of another gene from another parent. And because he's doing diploid genetics, this could not have been trivial, but he was seeing it. And there's a couple implications there. One is that it occurs not just on extreme mutant alleles that we make in the lab, it occurs on alleles of genes that are out there in natural populations that carry natural variation. And therefore, it may underlie a lot of genetics, as we realize. So genetic interactions might underlie a lot of genetics. So anyway, there's a lot of combinations of genes. So there's 6,000 yeast genes, so there's 18 million gene pairs. lethal mutation with the query strain that they were looking for. So they started off with query mutations in BEM1 and BEM2 that are involved in blood emergence, and they mutagenized those strains with levothyroxine, and they found synthetic lethal interactions with MSP1. And this was the first strain. It took a couple years to find that one synthetic lethal interaction because of that. And so the beauty of this set of viable deletion mutants is that it opened the door for systematic genetics. And so we can now have a matrix of 5,000 mutants, and we could cross any mutation into that whole set and make 5,000 double mutants. Because we can make temperature-sensitive alleles of the essential genes, we can also look for synthetic lethal interactions, just like David Botstein and Pierre Novick did by mutating essential genes, getting TS alleles, and then doing a process at a permissive temperature that cells are still alive. They carry a mutation that compromises the essential gene function. And so this is where Brendan and I got together because we started to think, well, we knew that the yeast community was creating this reagent set, and we started to think, well, the double mutants are going to be the most fun, and so we'll try and set up the system to make double mutants. And we can do it because yeast genetics is just so easy to do. And so I often wondered, why did I spend 5 years of my life studying yeast mating as a young adult, when I should have been studying money, right, and making money, like my brothers did. But in the end, if you study mating, then you can figure out how to make lots of double mutants. So I can't make millions of dollars, but I can make millions of double mutants. And so then we can explore mating functions synthetically value. So we can cross this and find these things. And so the way we think about it, and again, this is just a model, is that if you have two pathways like homologous end joining and homologous recombination and non-homologous end joining, and they both impinge on an essential function, you can tolerate a mutation in one because the other's still functioning, or this one, the other's functioning, but a double hit will kill the cell. Okay, so this is a synthetic interaction, and it often occurs between sets of genes that are encoding molecular machines that work together to drive essential functions. So if I remove one component of this machine and I screen all other genes for synthetic lethal interactions, all of the synthetic lethal interactions with all the components of the backup pathway. And that's true for this component and this one. So then genes that have similar patterns of genetic interactions are in the same pathway or complex. And so again, protein complex, we can often see if these two complexes are working together, we'll see coherent sets of synthetic lethal interactions between all the components of the complex. And they can be strong or they can be weak, but they're all coherent, so we know they're true, they're statistical. So Harvey won the Nobel Prize for his cell division cycle. He was really interested in synthetic lethality, and he articulated these two concepts around 2000, so about 20 years ago. And one is that if you have a cancer pathway that's a non-essential gene set, and you can then kill cancer cells specifically by targeting synthetic lethal interactions that take advantage of those vulnerabilities in a cancer cell. Okay, and that works like mad. Everybody's going nuts with this now because when he talked about this, he couldn't do any type of genetics in human cells, but CRISPR is just so obvious that this can be done. All those arguments you can use to work supplies and just replace human cells somehow, but now you can do screens like this and find it. The other idea he talked about, which is even wilder, is this genotype to phenotype potential. And so he was thinking of, okay, now we're going to start sequencing everybody, we're going to get their whole genomes, and then we have to interpret it, and we'll have to interpret natural variation. And if natural variation can combine either as digenic interactions or trigenic interactions to modulate pathways and lead to inherited phenotypes, we have to know the rules of how genetic networks work, right? And we have to figure out how prevalent it is. So, and that's a wild idea. I'm trying to prove it because we win our grants and we cite the Harvard's paper all the time. We say this is why we should give us money to do this. But there really is almost no evidence of genetic interactions associated with human genetics. And the reason is because it's a statistical game that we can't win. 20,000 genes, 200 million possible gene pairs, and if you look for, say 1,000 people in a GWAS study, you just don't have enough statistical power to find a single genetic interaction. And even more than that, when you think that if the genetic interactions are mapping, say, two different pathways that impinge on something that's important for disease state, then there's many different pairs of genes that will lead to the same phenotype. So you're trying to find multiple different pairs of genes that are associated with a disease state, right? And so that's another thing. And Eric Lander, so there's this missing heritability for any human disease, and this is where I don't know what I'm talking about very much, except for what I'm saying. So bear with me on that. But for any disease you look at, usually we only can explain about 20 to 50% of the heritability. All that's missing, and there's many different thoughts about this. That it could be rare mutations, blah blah blah. You just don't know what's going on. But it's quite possible, and it looks from these models that definitely genetic interactions are going to be some significant component of that. That being said, there's almost zero evidence for it. And Eric Lander watched this is why he's like missing heritability. He's going phantom heritability because variation is in everyone. skip something, but so, then I can go to the highlights. Anyway, we really, Amy Tong was a graduate student who started this. She's on this picture, but then Michael Costanzo took it over. We have a team of technicians, and they feed these locally designed machines to just make all the double beams, so we can just replica plate, and it works. The computational analysis is the tricky part. Chad Myers was in Olga Troyan-Sky's lab at Princeton, and he has a team of postdocs, graduate students. Anastasia was a graduate student with Ben and I, and she's now at Caltech. These guys really formed a team, and it's very simple. Our model for how to score a genetic interaction. If you delete a gene and you reduce the growth rate, but you don't kill the cell by a defined amount. So this one reduces to 0.7. Delete this gene, reduce to 0.5. If I delete this gene in this background, I expect to see a reduction of fitness by 0.5. Okay, that's our working model. So the fitness of the double mutant, the combination of the two single mutants, we expect to lead to a phenotype of 0.35. So synthetically value, if the double mutant is dead, then that's a negative genetic interaction. But if the double mutant grows better, then we'd expect that we call that a positive genetic interaction. So we quantify negative and positive genetic interactions, and we do it just by looking at colony size on a plate. And there's all kinds of systematic errors that we go from noisy data to data where we normalize, where we and get the true genetic interactions. So then, basically what we get is a vector of negative and positive genetic interactions. So I delete gene A, and if it shows a positive genetic interaction with B or with C, and a negative with these other guys, we score it and we quantify it. And we do that we cross gene A to all 6,000 other mutants, and then just for these things. And basically, here's an example. So RAD52 is involved in DNA repair, and we have negative interactions with all kinds of genes that have very well-defined goals of DNA synthesis and repair. So you connect, in general, functionally related genes. I mean, there's noise in the data, and if the gene is a signaling molecule that controls many different pathways, then you connect that signaling molecule to many different pathways. But if you're a focused player in the cell, then you end up connecting it to other focused players in the cell. And so genes that are in the same pathway have very similar genetic interaction profiles. Okay, so it's easy for us to define functional modules because we just cluster the genetic interaction profiles. And if we have two pathways that are backing each other up, then we'll see that they share synthetic lethal interactions, and it's a coherent set. All the components of each pathway will, most of them. There's always some false positives and false negatives in our noisy data, but we'll see lots of connections more than you expect by chance. I've drawn positive interactions between these components because if it's a non-essential pathway, that's what we see. And this is just because of our model. Basically, if you have a non-essential pathway, you kill the pathway if you delete a component, and then the double mutant looks just like the single mutant. Okay, so the double mutant looks just like the single mutant, not like what we expect. So we score that as a positive genetic interaction, just simply part of our model. But if it's an essential pathway, you have two essential pathways backing each other up. If you combine two TS mutants in the same pathway, the cells often die. So you see negative within and negative between. So we look for these types of network motifs, and I'll come back to that. But in order to create that graph I showed you at the beginning.